in making for over a year, and for a variety of reasons, like including COVID and so forth, it kept getting postponed. We wanted a face-to-face event, but unfortunately it wasn't feasible, and we thought we might as well do it. And since this year, Helen came to our exec, and then I asked Helen whether she would take over this, and she did, and it is here. Like, I mean, it's a great sort of program, and I look forward to a successful outcome. Also, I would like to thank Data61 for coming on board here, and Sharif and Saeed and Clara, everyone, to be so proactive, and Nigel guiding us through many of the logistics and other insights into how to do a nice workshop. So thank you all. Now, today I'm hoping that besides the technical stuff, you get a lot of opportunity for networking, identify people you want to work with, identify supervisors with who you want to generate PhD projects, especially Data61 and UNSW academics. These are some of the focus points. So I'll get on to introducing Professor Rakesh Verma now. I met Rakesh a few years back at CCS and came to know about the fantastic work he was doing, and especially the amount of data he has for cybersecurity and stuff. So I'll do a very quick introduction. So Rakesh is a full professor of computer science at the University of Houston and leads a lab called ReDAS. He's received a Lifetime Mentoring Award from UH in 2003 for mentoring undergraduate students and researchers. He's been a program chair of 11th and 12th ACM CODASPY conference, which is a very high quality conference. Also, he's co-author Cybersecurity Analytics books, Distinguished ACM Speaker. Also a Senior Fulbright Specialist, holds B.Tech degree from IIT Varanasi and research degrees from SUNY, New York. He is also a Catacosinos Fellow. So you can see he's got a very distinguished track record, and the topic today is phishing through the data science and human lenses, progress and gaps. So over to you, Rakesh. Thank you very much for joining us.
Thank you very much, Sanjay, for inviting me, and thanks to all the organizers for giving me this opportunity to share my work with you all. So let me start sharing my screen.
Yep.
And can you see my slide now?
Yes, but it needs full screen. Probably it's not blown to full screen yet.
Is that better?
Yep, that's good.
All right. So thank you very much, and I'm going to start my talk with an acknowledgement to the U.S. National Science Foundation, who has funded much of this research. As Sanjay mentioned, I'm reading the Reasoning and Data Analytics for Security ReDAS lab at the University of Houston. And the work that we have done and I'm going to talk about is a joint work with my students and many collaborators. So a quick outline, I will start with some motivation and examples. Quickly look at some phishing detection work, and from there I will move on to dataset quality issues, and also the book that we came out with, Cybersecurity Analytics, and hopefully I'll have a sufficient time. I have quite a few slides. I think the second half of the talk is even more interesting than the first half. So hopefully there'll be plenty of time for discussing the, systematization of phishing research work that we did. And also we came up with a benchmarking framework, version 2.0 of PhishBench. We are planning to make it public very soon. So it's an exciting and also, challenging time. We did several human studies, and I will also discuss a meta-analysis that we carried out recently of studies by other researchers as well as, our studies. And I will wrap up with, a few words on proactive versus reactive security and give some directions for the future. So here's an example, actually two examples, one on the left and one on the right. The first one, the one on the left, I call it a phishing email attack, and the one on the right, a spearphishing email. Could be also, a messaging text attack. So on the left, we have this email example that was inspired actually from an actual email that I received from a student who had taken one of my courses, almost a year before the email arrived. And I was wondering, why this email suddenly. The student has taken the course and successfully finished it. That got me thinking a little bit, and I started looking at the email the header, the metadata information that we have with an email. And, sure enough, it was not actually a genuine email. It was an attack. And there was a malicious attachment that, because I realized that it was an attack, I stopped, I deleted the whole email. Although, I try to preserve as many attacks as possible, some attacks I feel are not worth preserving. On the right-hand side, we have this spearphishing email. So the reason we call it spearphishing is because it has a lot more customization. This email actually, one morning I received it, and I was checking my emails on, my cell phone. And on the cell phone, you get even less metadata, even less, fewer fields from the header are shown when you are looking at it on the cell phone, because the screen is much smaller. And so this email said that I'm in a meeting right now, and so I can't call you. Do you have a minute? And, it was signed at the bottom with the name of our current head of computer science department at that time. It was Jaspal. And, I said, sure, what do you want? Quickly, this reply came back, can you buy a gift card from Amazon? Then the alarm bells started ringing, and I started looking at this email header more carefully. I opened my desktop and looked at the header, and then I realized that somebody had created an account, using the first and last name of our chair as the ID, and also signed carefully at the bottom with the first and last name of the chair, and so on. So this was also an attack, and I refrained from sending any gift card to anyone. But I was told by my colleagues that similar attacks have succeeded in the US and some other countries as well. On several faculty members, even in computer science departments. So, these kinds of attacks, we are all familiar with, most of them. And, you might think, why work on phishing? So I have listed a few famous attacks in the past that have happened. For example, the Sony Pictures data theft, approximately 100 terabytes of data was stolen using a spearphishing campaign. They gathered data from LinkedIn about the employees, Sony employees, and then used that to customize the attacks. Then there were, attacks on both Google and Facebook, where roughly $100 million was stolen using what is called business email compromise, basically fake invoices for computer parts. And over a 3-year period later, the attacker was arrested and is serving 5 years in jail now. Then there is the Ukrainian power grid attack, where 3 substations of the Ukrainian power grid were brought down using malware to automate power outages. And, it was basically a phishing email sent to employees of the Ukrainian power grid, and a nation state is suspected as the attacker in this case. And I attended the FBI InfraGard briefing on this, and they, explained quite carefully, how things worked out and how the grid was brought back after cleaning and isolating the machines and everything. And a statistic from the FBI Internet Crime Complaint Center from 2020 is that $4 billion worth of internet crime. Of course, phishing is a component of internet crime, and it's also a significant contributor to this $4 billion in damages. And if you're curious about, who is targeted by email-based phishing and malware attacks, you should see this paper in the Internet Measurement Conference in 2020, so quite recent, and pretty large study. Very interesting findings. So quickly, I have been talking about this, looking at an email header, and some of you, may be more familiar with the typical fields that we see, which I have shown on the right. The typical fields are the from field, the reply to field, the to field, the subject and date. And even some of these fields are not shown when you're looking on a cell phone screen at the email. Now, if you actually look at the original header, it has a vast amount of information in it, and I have color-coded the information based on how much we can trust it. So the information on green is, closer to the recipient of the email, so the receiving mail transfer agent, as it's called. And then, the fields from the submission engine, the mail user agent, and the sending mail transfer agent, those are shown in red and yellow because those are less trustworthy, right? Until the email has left the domain of the sender has quite a bit of control and can fake many of the fields. That's why some of the fields are shown in red, some are shown in yellow, and some are shown in green. Now, we did some work on email masquerade attacks, which I'm going to talk about a little more in detail later. And we found out that, people hardly even look at very carefully the typical email header fields. So, and very rare, email users will actually look at the email header in so much detail. Now, of course, if you're doing email analysis on cell phones or text messages analysis, right, SMS attacks and so on, then you have very little metadata to work with. So that becomes even more challenging. So I will talk about some work that uses only the text fields in a bit more detail later. Right now, I have given an overview of the solutions that have been proposed for phishing and spear phishing. So there are the popular whitelisting and blacklisting approaches, which are simple in concept and also efficient if you can do the matching quickly, if the lists are not too long. But you need to keep updating these whitelist and blacklist, and the updates are hard to automate, right? Even though some researchers have tried to do that, but still remains a challenge. And then of course there's the work on machine learning and template or pattern or rule-based pattern matching. So where you're trying to actually learn from attacks, learn from the data. But there are significant issues that the data that you train on, the distribution of that data is going to be different from the data when you actually deploy the model, because attackers are constantly trying to defeat the machine learning models. And so we call it an adversarial scenario. Then there is, of course, the issue of data quality. How good is the data that you train on? And other issues such as the speed of training, the speed of test time, classification, class imbalance, right? How many phishing emails versus how many legitimate emails. This is also called the base rate problem or base rate fallacy. And then, of course, we have the last line of defense, the humans. So people have proposed training. We also have some mandatory training at the University of Houston where we have to watch videos and answer questions, do a quiz. And people use all kinds of tricks, to avoid watching those videos. They found them very boring. So effectiveness of the training can be a serious issue. So these are some of the solutions that have been proposed, and I'm going to devote more time to the machine learning and the training aspects or solutions in a bit more detail. So let's get started with the phishing email detection. And there is this algorithm that we proposed called PhishNet-NLP in 2012. And this was a comprehensive solution which involved header analysis. We extracted the links from the email and we used a link analysis, basically a Google search with the extracted link and keywords from the email body text. And we had text analysis. So we had 3 different analysis subroutines or judges. And we also introduced context analysis in this paper, where we said that we can take advantage of the users' email that are sitting in the inbox or the sent box, the sent emails. And so we said if the email in question that we want to classify is very similar to the emails that are already there in the context, the sent box or the inbox of the user, and if we have a label for them, then we can use those. And so that's what we call context analysis. So I'll show you some results with and without context analysis, so you can see how well that works. In the header analysis, we did a little bit of path analysis, the path that the email takes from the sender to the recipient. And we also looked at authentication fields like domain keys, identified mail, DKIM signature as it's called, sender policy framework, SPF, and DMARC. And the text analysis was doing verb scoring, because we said that, the phishing email will require some action on the part of the recipient, either clicking a link or downloading a malicious attachment. So therefore, we started part of speech tagging the body text. And then after part of speech tagging, we identified the verbs and started scoring the verbs. And we adjusted the scores of the verbs based on whether there was a link nearby, or there was some kind of threat or urgency, like you must do this within a week, right? Phishers typically give you a deadline. And we also wanted to use named entity extraction, but we found that emails were too noisy and NER techniques were not working well on emails. So we decided to avoid using named entity extraction. Named entities are basically phrases that denote people's names, organization names, and so on. So proper noun phrases. And we for the data sets, we found this phishing email data set that Jose Nazario had been sharing. And we combined that with 1,000 legitimate emails that the 3 of us contributed. Essentially, we distributed the software and ran on our emails, so that way the privacy issues did not come into the picture. And here are the results of how this worked. So focus on the top left box first, where we show 2 different runs with 4,550 phishing emails. And the first set of columns, 4 columns, is without context, the leftmost set. And then on the right, we have with context. So as you can see, the overall accuracy or detection on phishing emails, this is the very first column in bluish purple. And then after that, we have the header analysis column, then the link analysis, and finally the text analysis. You can see that the context does improve the detection rate from overall detection rate from 97.7% to 98.1%. And you can also see that the text analysis improves the most on the context analysis, obviously, because that's the one that uses the context analysis, really. The header and link analysis, they don't really use the context analysis, so they remain the same. And if you see, the text analysis is lagging behind. the header and link analysis. But as we know that, the header analysis is, the header is under control of the sender, until the email leaves the sender domain. So we have to be careful to trust it completely. And also the link analysis, we cannot look at exhaustively all the results that are returned. So we are looking at just the top 30 results after the Google search. So we cannot trust it completely also, even though the accuracy is pretty high. And then if you look at the bottom right corner, you will see again 2 runs with 1,000 legitimate emails. And you will see that we are misclassifying 8 emails out of 1,000, 99.2% accuracy on the legitimate emails, and 0.8% misclassification rate without context, and that drops to 0.7% with context. So the context helped, a little bit, but not too much. There was not too much room anyway. And I don't have time for the other 2 boxes here. If you're curious, you can take a look at the paper. So I will move on to the text analysis, because that was the one which was lagging behind the other 2. And so what we did was we used the t-test combined with semantics to look at the emails, significant differences between the phishing emails and the legitimate email bodies. Now we are no longer doing header analysis. We are not doing a link analysis. This is purely body text analysis. And the way we are using semantics is, again, doing part of speech tagging, incorporating sense learner to find out the sense of the word. For example, the word bank can be a financial institution, or it can be the side of a river. So we need to distinguish between the correct sense of the word bank. For example, many of these phishing emails contain financial institutions. And finally, we augmented our basic pattern matching classifier with part of speech, sense tags, as well as WordNet relations. So WordNet is a nice knowledge base that is available online from Princeton University, and you can also get the WordNet API. And it has a lot of interesting relationships between, nouns, between verbs, adjectives, and adverbs, right? Those are the 4 classes for which WordNet has information. And what it does is it organizes the words into what are called sets of synonyms based on the concept. And then it links the synsets. For example, for nouns, you have what is called hypernymy, hyponymy relation, and also meronymy relation and other relations as well. And for verbs, even a richer class of relations. So we try to take advantage of these relations to make our classifier more robust, because we said that the fisher can keep varying the syntax, right, as long as the meaning is preserved. And so we need to catch the meaning. And so we designed 4 different classifiers. The basic classifier was just pattern matching, and then, augmented with more and more information as you go up the pyramid. And the results were quite interesting. The phishing data set was the same as the previous work. But the legitimate emails set is much bigger now. We discovered the Enron email data set that's available online. So we used 10,000 emails from the inbox of the Enron employees. And we also used 4,000 emails from the sent mailboxes. And the interesting thing was that we wanted to do a generalization study. So we said we will not train at all on the sent emails, and we will just test on them. And for the inbox emails, we use 70% for training and reserve 30% for testing. And we did the same thing, 70-30 split for the phishing emails. And if you look at the results, you will see that the first column, which is for the phishing detection rate, higher is better, higher values are better. So we are getting, just with the basic pattern matching, almost 93% detection rate. And as we go on increasing knowledge, we get at the very end 95% detection rate on the phishing emails using what we call an action detector. And we also had a nonsensical detector. And, you might wonder why we needed a nonsensical detector. We think that this may be due to data poisoning attacks. So there were emails where, random dictionary words were thrown into the email body. And also there were emails where passages from popular stories were dumped into the email body, along with, a subject saying your account has been suspended, go here, and then giving a link. So we, separated out our detector into two parts and trained them separately, sequentially. So we first trained the action detector, and then we train the nonsensical detector on the misclassified emails when we are doing our training. And you can also see that there is this class other, and so more details about that in the paper. But we got dramatic improvements using this kind of statistical t-test combined with semantics, both in terms of phishing detection, but the misclassification rate is a little bit higher now. So on the inbox emails, it goes from about close to 5% to about 2.2% or so. And on the sent box emails, so what was most interesting, we didn't train on them at all, but still we got a lower misclassification rate on those emails, like 4% on with the basic pattern matching classifier, and a little bit higher, with the WordNet. And we saw an interesting pattern where, adding the WordNet relations make the phishing detection improve, but also degrades a little bit from classifier 3 on the inbox and send box, the misclassification on the legitimate emails. So moving on from the phishing emails to a little bit about data quality. So, because we started wondering about these emails when we took a careful look at some of the emails that were being misclassified. We found that some of them had no body text at all. And so, this becomes a question of whether you are missing the data or, this is real data in which the attacker, just send the email with just the subject line in an empty body. And so, I have listed some key desiderata for data. Definitely availability is a big one of them, because, how to get hold of private data sets, right? That becomes a big issue. And then, of course, you want to make sure that you do have current attacks in your data set. So that's currency. And at the same time that you have current attacks, you also want to have classical attacks, because you don't want to fail on the older types of attacks, just because your machine learning algorithm was trained on more recent attacks. And so diversity is also an issue. And then, of course, integrity and completeness of the various fields and metadata. Now, in security, we can never have completeness of attacks, because the attacker is constantly and continuously trying to defeat the machine learning models. And I have listed two other criteria: representativeness and data set difficulty. And the most interesting one and the most, I would say, important one is the data set difficulty, because you don't want that your data is leaking so much information, that's an artifact. And that artifact is causing the classifier to do well. So, for example, one of my students reported 100% accuracy, and I said, did you take a look at the data set? Because I was mystified, on the 100% accuracy. And then we found out that the data set for phishing was, over a certain period of time, and the data set for legitimate emails was on a totally different period of time. There was no overlap between the two. And if you start extracting all kinds of word sequences from the header as well as the body, then the classifier can quickly pick up on the year as the most significant one for getting the correct classification. So, we designed small data set experiment, as I call it, where we take a very small portion of the data. We train on that. Of course, we take several random samples, but very small samples. And we train on those small samples. And then we look at the accuracy and F1 score and all the other metrics on the rest of the data. And so, if we find that we are achieving very high accuracies and F1 scores and so on, with very small amount of training, then that is definitely something suspicious and worth looking into. So, when we created these data sets of, emails from various sources, such as WikiLeaks and also Enron and so on. And we created data sets of emails with headers, without headers, and we organized this first anti-phishing competition in 2018. And one issue that we found, was that the information leakage from the headers in our version 1 of the data set was significant. And this we discovered by the small data set experiment that I mentioned just now. And so we went into further rounds of cleaning, normalization of the header fields, IP addresses, and so on. In the current version that we are distributing publicly is version 2.1. And, the without headers data set, the small data set experiment shows that, there is, it's a very good data set. It's a pretty challenging data set. And with the version 2.1, the emails with headers also don't have as significant leakage anymore. We also looked at intrusion detection data sets and malware data sets, but I don't have time to talk about those today. We found several issues with the intrusion detection data set that I've listed here, and I've given the reference for the paper if you're interested in the malware data set that we analyzed. It was an industrial data set, a real malware data set from deployment. And so data set quality is very important if you're training from data, if you're trying to learn from data. And, I want to now discuss a little bit about, the latest work on phishing emails, where we used quite new features. We used stop words, punctuation, word counts, and also unique versions of these, where we, look at unique words and so on. And so there are quite a few features that are inspired from these, syntactic components of an email body. And we did two kinds of experiments. We weighted, the phishing emails because the data set is unbalanced that we created. We have one phishing email for every 9 legitimate emails. So we decided to do both weighted and unweighted experiments where we take into account this class ratio, which is imbalanced. And the version of the data set we are using here is InspireP dataset version 1, but no headers. So we are only doing body text analysis. So the leakage, information leakage from headers is not an issue here. We found that creating an ensemble using the 14 best base models, where we actually do an ensemble using learning models based on the base model probabilities as features. That gave us the best results. So that was pretty interesting. And this work you can find in the IEEE ICDM workshop proceedings in 2018. And it's remarkable in the sense that we are not really using the semantics in this case, right? The first two techniques that I talked about were using semantics. And so there is hardly any use of semantics, and we believe that still the method is quite robust. And so that's all the phishing email detection work. And now I'm going to move on to phishing URL detection. And for phishing URL detection, I will quickly mention a couple of works. So on the right, you can see the parts of a URL that are significant. For example, the top level domain name, and of course the country code also is there if it's not the US, and the internet protocol field, the host name field, and the path. We are using information just based on the URL alone. So we are moving away from doing Google search or internet search. And you might wonder why we are moving away from that. Well, there were several issues with doing a Google search, right? Google started rate limiting our automatic searches from our program, and then it would also, block us for a day. So we could not run our experiments. And then later on, Google went ahead and deprecated their API also. So we said, okay, let's not try search anymore. And let's just see whether we can classify a URL just based on the character information, things like @ period, all those slashes and so on. And of course, the letters and digits and so on. So we designed statistical features of character distributions in the URLs. Looks like maybe there are some questions in the chat. Should I look at them, or?
No, once you've, Rakesh, once you finish your talk, then I will probably relay the questions to you.
All right, sounds
unless it's convenient for you to look at yourself. Up to you.
Thank you, Sanjay. So I will skip it for now. So we designed statistical features of character distributions where we compare the character distribution in the URL against the character distribution for standard English text that you can get online. And we use features like KL divergence and KS test and so on, statistical tests. And those gave us very good results. We supplemented them with features such as edit distance and also normalized character frequency. So we used a small whitelist, to identify targets in this case. So therefore, fast target matching with the Aho-Korasik multiple string matching algorithm, we used it for this work. And there are some other features that I don't have time to go into. Here, we managed to get hold of 4 different data sets. So we were able to do a cross data set study as well as a total data set analysis. So I won't be presenting all of the results today, but the best classifier was, in this case, the ADA boosted random forest classifier among the classifiers that we evaluated. We presented this at CODASPY conference in 2015, where you can get all the details of this work. Moving on to the second work that we did on URL detection. Here we used character engrams, so sequences of characters of length 1, 2, 3, and so on. And we went up to, I think, 8 or 10 as the maximum n value. And we used online learners in this case. So adaptive learners, which try to learn from every example and suffer a penalty on misclassification immediately. If they misclassify something, then they suffer a penalty and then they try to learn from that. And so, we looked at, balanced versus unbalanced scenarios. So we had 1:1 phishing to legitimate, and also 1 phishing for every 7 legitimate URLs. And we also did a live URL experiment to see how good it will perform. These techniques will perform if we don't train on the URL. So we just collected for like 24 or 48 hours URLs from PhishTank and also legitimate URLs, and then try to study how well the techniques work on live data sets. So 0 hour or a 0 day attacks, for example. And so we got quite impressive results with two different online learners. The one called AROW, Adaptive Regularization of Weights, and the other CW, Confidence Weighted Online Learner. So those two were the best. And a little bit about phishing website detection. So we looked at—
Rakesh, could we wrap up, please, and leave some time for Q&A as soon as you could?
Oh, are we out of time already?
We are leaving about 10 minutes for Q&A.
Okay, I see.
Yeah, I mean, just finish it, whatever. We can exceed a little bit, that's okay.
Okay, all right. Okay, sounds good. So a little bit about the phishing website detection. We used several new features and different classifiers, and we did quite a few experiments. We got very good results with for low false positives. I will move on in the interest of time to adversarial machine learning work that we did, where we investigated the robustness of the RCNN model for phishing email detection under 6 different test time attacks. So no data poisoning for training, but during the deployment, we considered 6 different attacks, and I've listed them here. And we found that the RCNN model is pretty robust. So you see the ROC curves here, the receiver operating characteristic curves. And you can see that there is very little separation between the original versus the other curves when we do the attacks. The best attacks turned out to be the relationship-based attacks for the RCNN model. So it's pretty robust. It's a combination of the RNN and the CNN. So 2 different deep learning architectures. And I want to mention that all this work got me interested in how do you adapt the data analytics techniques to cybersecurity fields, because direct application does not work so well because of the active attacker and other things. And so we came up with this book, Cybersecurity Analytics, where we are hoping that this will inspire more collaborations, a common vocabulary between data scientists and cybersecurity experts. And so it will spur more research in adapting data analytics for cybersecurity. So I'll just quickly mention the systematization of phishing research literature that we did. We looked at approximately 300 papers, and for the phishing detection work, we looked at the cybersecurity needs, and the other dimensions were data set, features, algorithms, and what were the evaluation scenarios and metrics. And you can take a look at this paper, and you can see some of the key findings and the key papers that we identified. And for the human study, we looked at the goals of the study, the setting, the population, and the various variables, the context, whether it was phishing email or website, and also what kind of experiment design. So in each case, we identify the key papers. And the key takeaway for detection papers is that more than 80% of the papers use unrealistic scenarios, right? For example, balanced data set, inappropriate metrics, old data sets, or completely ignoring the attacker, no generalization, no zero-day experiment, no security analysis. The key takeaway for the human studies is that 60% of the studies have small number of participants. And there is also the multiple comparison issue, where, if you do several different hypothesis testing on the same set of data, then, the chance or the probability that one of them will come out significant rises a lot. So because of that, people have proposed corrections to the p-values, such as Bonferroni correction and Benjamini-Hochberg correction, and so on. So very few people do those kinds of correction. Quickly, a word or two about the PhishBench architecture. So I've shown a pictorial description of the architecture here. And we have a lot of metrics available, more than 200 email and URL features. And we provide several models, including deep learning as well as classical models. and we do scalability and class imbalance studies of all these models. And then we compare with the models that are available for things from AutoML and Teapot, for example, which try to find the best architecture given your data set. And this is reported in IEEE Access in 2020. And then coming to the training work, which is the last line of defense, right? No amount of technological security will be sufficient if someone downloads a malicious email attachment because either they are unaware or they have deadline pressure. So we did a study of the University of Houston population after Hurricane Harvey. And we found that over 6% of the respondents admitted to clicking on links and downloading attachments that they otherwise would not have done. And you can find this work in IEEE Explore. We also looked at how people identify whether something is fake or not. So we created, using NLG technology, natural language generation technology, the recursive transition networks in particular, we created synthetic data of Hillary Clinton and Sarah Palin emails. And we combined them with real data. Of course, we gave some training samples to the participants in the study, and we wanted to find out if they can then distinguish between the real emails of Hillary Clinton and Sarah Palin from the synthetic ones. And we found out that the overall detection rate was 52.94. So that's close to random guessing, right? Coin tossing. It was a small scale study in the lab. You can see that the Hillary Clinton detection rate is much higher and the Sarah Palin rate is lower. And there is a significant difference between the Flesch-Kincaid level. The Sarah Palin emails are harder to read versus the Hillary Clinton emails. And you will also notice that the people who had higher confidence actually did worse on the detection rate. And then we followed up with a larger study of more than 2,000 participants, where we got close to 2,000 valid responses. And we were interested in finding whether attackers can use professional networks like LinkedIn and versus Gmail to increase their success rate. So what we found was that mobile users did much worse than participants who used personal computers. And we found that company representative fraud can still deceive quite a few people. Only 26% of the participants were able to label all 4 fake offers correctly. And again, we used the recursive transition network to generate fraudulent emails. And we found that including the sender and receiver information in the email increased the success rate of the attack quite a bit. And we also found significant correlation between the clues that users pay attention to and their performance on detecting attacks. So more clues, better the performance. A quick word about the meta-analysis that we did recently, where we examined several human studies papers, and we found actually that the big challenge in the literature is that effect sizes cannot be calculated because there is not enough information in the papers. So this is a big challenge for meta-analysis, but we were able to use 37 papers in the meta-analysis, and we found that there is a significant relationship between the participants' age and their susceptibility. Females are more susceptible than males, and user training does help. And you can see this online in the archive. I will close with proactive security. So we are trying to generate attacks now, not just to improve humans, but also to improve detectors. And we found that semi-automatic attacks can fuel humans, and automatic attacks have a coherency issue. But automatic attacks can help detectors quite a bit. And so we have some interesting results with the GANs in imbalanced scenarios, which are under review. And there is one paper published already. So I will close with the key takeaways and some directions for the futures. So although there is significant body of research on phishing detection and human studies, we still have room for more research that takes into account the needs of the cybersecurity domain and the human in the loop. And human behavior changes based on the device and the environment. Things like, for example, the stress due to Hurricane Harvey, or maybe deadline pressure. So can we design systems that can sense this behavior change and adapt based on that, right? Maybe they can adjust their thresholds and become highly sensitive if the recipient is stressed. Finally, there is evidence on what works in detection and how systems can help, right? The last line of defense. Now, what we need is to put it all together, and that will make for a really good system. And I will thank you all for your time and attention today. And thanks also to all my collaborators and students. Hopefully, we have still a few minutes for questions. Thank you.
Sure. Thank you, Rakesh. So very quickly, there are a few interesting questions. One is from Arindam Paul from Data61, and he's asking, like, the algorithms using certain rules for detecting specific patterns, if we design it in such a way that they are with the existing data and the phishing attackers change the data, then those rules may not be valid. So what do you think about that?
Yes, that's a very good question. And that's one of the reasons why we included, sense learner and WordNet relations to try and expand so that it's not purely syntactic analysis, right? Even when we are doing syntactic analysis, in the work where we use stop words and punctuation and so on, we feel that, it's pretty hard to, get over that unless you have, long rows of punctuation and stop words that you disguise using, coloring of the background, using the color of the background and so on, tricks like that. So, we feel that we have paid quite a bit of attention to robustness in our patterns. And so that's something that you also see in the adversarial machine learning work that I talked about, where we create 6 different kinds of attacks and then try to study the robustness of the RCNN model. So this issue of the active attacker is definitely something that we all have to pay significant attention to in designing our algorithms and methods, and also data sets when we are creating our data sets. And that's why we are interested in creating automatically or semi-automatically new attacks. So that way, we can try the detector on these new attacks, the attacks that the detector has never seen before, and without waiting for the attacker to defeat our methods.
Right. We have next question from Professor Toby Walsh, and he's asking, how is phishing in mobile phones, SMS, different from emails, especially that it's easy enough to spoof phone numbers? And you kind of touched upon that, so if you can say a few more words.
Yes, actually, that's a very good question also. There you have less metadata. In the case of text messages, and actually the metadata is in the recipient account, so you really have to access that, and so it becomes a really hard scenario where you have to rely basically on the body text analysis, and which is why I focused quite a bit on the body text analysis in this talk rather than link analysis and header analysis, because you may not have those things in a social network or on a cell phone. And as I did show that people are more vulnerable on their cell phones in the human studies part of the talk. And even I myself, was about to fall for a spearphishing example that I gave very early on. So that's definitely an area that is becoming, more active now. People are paying more attention to smishing, as they call it, SMS attacks. And so some of the techniques will carry over, some won't.
Okay, and we will take just one final question from Alfred. He says, can word vectors be useful for semantic similarity such as glove?
Yes, indeed, we have tried them. in our phishing work, as well as some other work that we are doing. And word vectors do turn out to provide, more than just, superficial contextual similarity, right? So, people have shown that certain rules can be done, with vector addition of these word vectors, vector addition and subtraction judiciously. And, so definitely, something to consider very seriously. And also in the first anti-phishing competition, several of the winning models did use word vectors.
Right. So I think we will probably circulate Rakesh's email IDs, and further questions can be sent to him later on, Rakesh, if that's okay with you. And in the interest of time, let's thank for what a fantastic talk and a lot of insights into phishing research for future. So please join me in thanking Professor Rakesh Verma.
Thank you very much, Sanjay, and thanks to all of you for giving your time generously.